Hello, we are back much earlier than I expected because I have been writing CSS all day and I need a break. So I'm going to take a 15-minute break, maybe stretch to 20, but we'll see how we go. Write some Fortran instead of CSS. So this is a series on Fortran, but also on the kind of problems you would solve with Fortran, so engineering problems. Now, if you were to walk into pretty much any engineering classroom at any university or college in the world and ask those engineers, what do you spend most of your day thinking about? I expect the majority would say that they spend most time thinking about finding roots. Finding roots is, something used widely in engineering. Engineers care a lot about finding roots. So we covered in the last video a very trivial, analytical example of finding roots for a quadratic, but there are many real world cases where we might want to find some roots. So we can think of open channel flow is an example. We have this thing called Manning's equation. This is the formula for it. You don't have to worry about too much. A is just the cross-sectional area of the channel. R is the hydraulic radius. You calculate that via some methods. S is the slope, Q is the flow, and this 1 on N is it's like a Manning's coefficient that you kind of get that experimentally, if my memory serves. It's been a long time since I've designed open channels. So imagine we have rectangular channel, it's width B. We want to find, if you want to find the normal depth, so a normal depth is basically the depth that the water is in the channel such that you have steady state flow, which is an important thing you want to design for. You can read more about that if it really interests you, but you kind of get an equation that looks like this for a rectangular channel. And we want to solve for dn because we want to know what the normal depth of flow is here. We can't really solve for this very easily. But what we can do is we can take this q here, we can rearrange this equation and subtract q and make this equal to 0. And now we've essentially got an equation that if we solve the roots for it, we can basically solve this equation. So if we want to calculate the normal depth, we can't really do that because it's a function of the flow, of Manning's coefficient, of the width and the geometric properties of the channel. S is the slope. It's a function of all these things, so it's not directly calculable. Another example, if you want the wavelength of a tide, you got this equation here which governs that. We can rearrange that so that f of L equals 0, and we get this. We find the roots of this equation, and that would give us the length of the waves. So yeah, as I said, simple case ax squared plus bx plus c has an analytical method. But even if we just change that and ax squared plus bx to the 1.2 plus c, or ax to the 2.6 plus bx plus c, these don't have analytical methods to solve them. Numerical methods are what we've got. So we use numerical methods to solve them, to find roots. Very common in engineering. Two people jump out of a plane, one after the other. You want to know when they're going to meet. Two equations are equal. That's also a root solving problem. So the simplest one is, there are a few ways to solve this. Bracketing methods are kind of one group of algorithms that we use to find the roots. So you imagine we have some graph. This is some f of x. It's potentially not even really necessarily a nice function, an x squared plus 3x or whatever. This is usually discretely calculated by subbing in actual values to an equation like this, or like this, and that's that is the equation for the line. But for something simple like this, we look at this. It's going to cross the x-axis at some point, possibly if it has roots. We don't know where it is, but at some point it's going to cross, and this is what we're trying to solve for. We're trying to solve for the roots here. So a bracketing method is very simple. You pick an initial guess, A and B, or lower and upper, they're sometimes called, and you want to try and bracket the root. So you want one on one side of the root and one on the other. So basically here, so f of A is greater than 0 and f of B is less than 0. F of B is below the axis. So we know that if the value of a function at some point A, whatever sign it is, whether it's positive or negative, in this example it's positive. If we take another point, say B, and we calculate the value of the function at that point, if the sign is reversed, the only way that's possible for a continuous function is if it has crossed the x-axis at some point. So we know the root is somewhere in between these 2 points, and that's why it's called a bracketing method. So obviously, you know, these methods don't work if there's multiple roots, or if there's no roots, or yeah, so they basically work as long as there is a single root. The trouble is you kind of have to guess A and B. That's like an initial guess. So bisection method is the simplest bracketing method. We have XL, XU, lower and upper. The midpoint of these is, you know, obviously just take the average. And so the algorithm looks something like this. So if the negative value of the function at the lower bound times by the value of the function at the midpoint. So this XL plus XU on 2 is just the midpoint. So A plus B divided by 2 gives us the midpoint. So we take the value of the function at A, the value of the function at the midpoint, and if they're the same sign, so that's why we take the negative of A and we times it by this, because 2 negatives will give a positive and 2 positives will give a positive. So basically is a way to check that whether they're the same sign or not. If they're both the same sign, so both positive in this example, if the midpoint is to the left of this root, then we know we can just move the lower bound up to the midpoint. Because if they're the same sign, it means the root is not in between them. So we can close that bracket on this side. But if the midpoint here, this is obviously not drawn to scale, is just the right of this root, they are opposite signs. So we know now that the root is between the midpoint and our lower bound, which means we can drag the upper bound to the midpoint and we narrow that bracket. So every iteration, the size of the bracket halves and you eventually converge on the root. So it's a very very simple formula. So basically if it's less than 0, then it means the upper, it means the root is in the lower section, so we can drag the upper to the midpoint. Otherwise it's in the upper section, we drag the lower to the midpoint. So this is kind of what it looks like here. Another example, XL is here, XU is here, first midpoint is here. Obviously we move the lower up here because the lower and the midpoint are the same sign, so the lower gets moved up. We now have M2, which is the next midpoint, which is still to the left, so we drag it up again, etc., etc. So we're basically gonna write this algorithm, this bisection method in Fortran. The code is actually like very simple. This isn't a complex program at all. We introduce a new concept, which is going to be loops. Otherwise, we're not going to see anything too new other than how to do loops in Fortran. We can terminate on some error tolerance, but I think for the sake of our program and for the sake of time, we'll just set, you know, a max number of calculations. But the fact that the bracket halves each iteration means, like, if you know some acceptable level of tolerance, like, you know, the measuring accuracy of your equipment you're using to even take these measurements, or, you know, maybe some like machining precision is like, any more accuracy doesn't matter. We can actually calculate how many iterations it's going to take us to get to that point. It's also worth noting that, like, a lot of these problems, given they don't have analytical solutions, the numbers are just going to be like, you know, arbitrary precision decimal places. So if you're trying to do floating point math, like, it's very rare you're going to get an actual 0 for the root. So, you know, if you get 0.000001 as a solution to your equation, like, you might as well accept that as a 0. So yeah, just go over this again. Easy, it'll converge. We have a known max number of iterations. There's some formulas here. You can even Google this if you really want. Disadvantages, it's slow. You have to know A and B, like your initial guesses. Like, you can programmatically search for them. Like, you can make A 0 and B 0.1 and, you know, increment B until you actually bracket the root. But yeah, in some sense, you have to be able to find A and B so that they bracket. Does not handle multiple roots. It's not smart. So because we're always taking the midpoint, like, if I try and find a graph again, like, if our A had been really close to this root, the value at f of A would have been smaller. The magnitude of the value at A would have been much smaller than the magnitude of the value at B, which kind of implies that the root might be closer to A than B. So taking the midpoint is, like, inefficient. It's obviously not always the case, depending on the shape of the function. Like, this one actually is pretty steep around the root, but if it was a much more gradual, like, slope near the root, like, yeah, we would have some information encoded there that could potentially lead us to fewer iterations. But yeah, the key one is it's, you know, very easy to implement. So let's go do this. So the trick with, like, most of these engineering numerical problem solving things that we do in Fortran is like you just follow the equations, or you just write the algorithm out by hand and you just code to it. So it's very, very easy. So let's get back to our program. We've already got our implicit none. So we're going to want some lower and upper. Call them like x low, x up. I'm just going to call them low and up actually. Sure, let's call it x low, x up. How about that? So A and B is what we also called them in our examples. So they're just like the upper and lower brackets. I'm gonna store the midpoint in another real as well. Do f of low and f of up. So this is the value of the function at x low and x up. Pretty straightforward. So this is like the actual value of the x-axis, like 1, 2, 3, whatever. This is the value of the function at xl. And I'm going to do an integer as well. I for our loop counter, and I'm also going to do a max iterations. Sometimes you'll actually see, I don't know if this is an actual convention, but when I used to do a lot of Fortran, like I used to use n for the maximum iterations. It feels a little bit confusing to me, like using n after all these years coming back. Like, so I'm just going to write max iterations. Fortran tends to like prefer conciseness, so like really short variable names. Like, but I write too much JavaScript, so that's broken for me. So let's do max iterations. This converges pretty fast. So I'm going to do like, let's just do 20 for now. All right, and we're just going to, same as we did last time, just input output via standard in, standard out. So provide initial guesses for lower and upper bracket. And let's read something in. So we're going to put that as in x low and x up. Now, so we basically want to do an if statement. So if f low times f up, so we're going to multiply them together. If they're greater than 0, that means they're the same sign, because they're either both negative, which is going to give us a value greater than 0, or they're both positive, which is going to give us a value greater than 0. So if they're the same sign, then we need to exit, right? So we need to write oops, star, the initial guesses do not bracket the root. Try again. So we're also going to see a new keyword here, stop. Basically just terminates the program. You know, we could check for 0, like on the off chance that someone guesses the root, but it's kind of not the point here. So I'm just going to leave that. Cool. So let's do so the next thing we're going to do now that we've got that is let's just check our algorithm. So we've checked. So we're going to calculate the midpoint, because the first thing we do is we use the midpoint. So let's do let's just do a loop. So to do a loop in Fortran, you write the do keyword, I equals 1. So that's the starting increment. And then, like, this is why people tend to use max iterations for n, because you've seen a lot of examples like do I equals 1 to n, and do, that's like the stopping condition. I kind of actually like max iterations. I feel it's cleaner, but you know, if you see do I 1 comma n, that's basically n is a stopping condition. It's just convention. But yeah, I'm used to writing code more like this today, so I'm going to do that. So the first thing we're going to do is calculate the midpoint. Actually, so in other programming languages, you might be used to seeing something like I++ or I equals I plus 1 or something inside the loop. If we're doing like a standard do loop in Fortran, I is automatically going to increment every time it gets to end-do. So it's going to do whatever's in here, and then on end-do, it's going to increment I and basically go back to the start. So we don't actually need to do this. So we're going to calculate the midpoint. So the midpoint is going to be x low plus x up, and we're going to divide that by 2. So that's our midpoint. So you could almost call that x mid, right? Let's call that x mid just to be consistent. X mid. Then we're going to calculate the f of mid. So I need to define that up here, f mid. Okay, so yeah, we need to pick a function. So what are we actually trying to find here? So let's do something like, let's just make this bigger. Oh. So if we have, you know, like f of x equals e to the minus x. Actually, no, let's do, what if we had an equation like this? X, I want that lowercase, x equals e to the minus x. So this is something that doesn't really have like an analytical solution. We can rearrange this so we can be like, you know, e to the minus x. And then we can like take x away equals 0. So now we have an equation, right? To find the roots of. We basically want to find when this equation is 0, and that'll tell us when x is equal to e to the minus x, which is what we're trying to solve. Like we're trying to find, okay, what values of x is this true for? Well, we rearrange this, we get this, we solve for the 0, and that's how we solve the original equation. So let's do this. This is a nice one. So, so our function is x equals e dash dash minus x, which is e to minus x equals 0. So yeah, let's do that. So f mid is going to equal, so there's a representation of e in Fortran, it's just exp, it's e raised to the power of something, so it's going to be minus 1.0 times x is x mid. So that's, there might be a way to just do like, you could even maybe do 0 minus x mid. I don't know. I'm just going to multiply it by -1 minus x mid. So that's e to the minus x, e to the minus x because x is x mid. So that's, we've calculated the value of the function at the midpoint. So let's go to our algorithm here. So we want to check if the function at the low point times the midpoint is less than 0. So let's do an if statement. If f low, did we already calculate f low? We didn't. Okay, we need to. So if f low multiplied by mid, I'm going to write it like this. So if we look back here, we're taking the negative and we're doing less than 0. I don't want to times this by -1. So if they're opposite signs, that's what this means, then they bracket. All right, so then if they're opposite signs, the lower mid are opposite sides, it means they bracket, which means the upper can now become the midder. So, sorry, the mid. So x up equals x mid. So we're just reassigning the value of x up that we read in from standard in to the value of x mid. We can do that, we can mutate values, no problem. X up equals x mid. And what we can also do is we don't actually need to calculate f up again because we already know the value of the function at this point, it's f mid. So we can just store that there. But I need to, for here, because f low doesn't equal anything yet. So what did we say it was? Let's copy paste this. Let's do this. This is going to be x low. This is going to be x up. I'm actually not sure why this is highlighting like this. I'm using CLion just as my text editor to write Fortran. If you're using like a proper Fortran IDE, like I don't think this would be a problem. This should still compile. We'll see when we go to compile, but I don't actually think that's an error because it's looking fine here. So let's just continue. So if they're on the same sign, do that. Else, if they're opposite signs, we know that it so xlow is going to equal to xmid. We basically do the opposite, right? Yeah, so it either brackets, in which case we drag the top down, otherwise it doesn't, so we move the lower up to the midpoint. And that's the algorithm, really. Let us, what can we do here? How about let's write inside this loop? So just some debugging, iteration. What else can we write? Let's write the midpoint. Do we want the midpoint? Let's actually write xlow, xmid, xup. Make sure that looks all right. Flow, yeah, let's do that. Oops, could have just done that all in one go. Oh well. And I'm actually just going to do just write a blank line here just for better formatting. And do. So that's basically how we do a loop. You see there's no like increment counter or anything. Cool. OS, cool. Alright, so we got the bisection here, so G Fortran -O bisection F90 compiled alright. So let us run this. So lower and 1, cool. So I picked 0 and 1 for my brackets. So in iteration 1, we've got a mistake here. Yeah, xlow has been overridden here, so I actually need to do that. I need to move this here. So if I do 1 and 2, or 1 and 21, cool. So we've tested that. 0 and 1. Let's see if this makes more sense. So in iteration 1, xlow is 0, 0.5. The f of 0 is 1. The f of 1 is -6. So we bracketed, that makes sense. F of mid is the same sign as low, so we want to move low up to the mid. That's worked. Calculates the midpoint correctly. They're now opposite signs, so we would expect this upper to become the mid, which it has. F mid is now opposite, so we'd expect the upper to become the mid. So yeah, that looks like it's working. And if we look at the value of F mid, like 0.1, 0.2, 0.089, 0.0072, like you can see these values are getting smaller and smaller, and by the end of it, you know, we're essentially like at 0, like 2.34 times 10 to the -7. You know, that's, you can see here, like it gets closer and closer to 0, but we're not actually going to hit 0. We could probably have stopped, you know, 10 to the -6, 10 to the -4. You know, we probably could have stopped around like iteration like 7, to be honest, or even, you know, here, depending on how accurate we want to be. But this looks like it's working. So yeah, very, very simple algorithm, very simple code. We've introduced the loop control structure. Yeah, that's it for this video. Nice and simple. I think next time I might maybe look at instead of input from standard in and standard out, like maybe we'll read from files, and maybe we will extract some of this into like a function that gets imported rather than just writing in main. Yeah, hope you've liked this. Hope you've liked the free engineering knowledge dump too. We're going to cover just as much maths and practical applied engineering as we are coding in these series. So hopefully you enjoy that. Let me know if anything's not clear. Let me know if I've missed out on a key Fortran feature you're aware of. As I said, I'm not a Fortran expert by any means. I'm more writing Fortran again because I want to solve these kinds of problems again, because it's been a long time. So yeah, let me know if as well if there's a specific algorithm you want me to look at. I can do that. Thanks again for watching.